Okay, so today we are going to study Greens Theorem. So remember, we had a long introduction, many classes about how to compute line integrals. We discussed the main method, which was about parameterizations. Then we said if the function is conservative, the integral is path independent. And that's equivalent to saying the integral over a closed curve is always equal to 0. And that's all done. Now, what is Green's theorem? So Green's theorem is mainly concerned with closed curves. So imagine you have a closed curve. You have a function that's smooth inside the curve. So this is, we call this the interior of the curve. We have a function that's smooth over that curve. So the function f is smooth. And remember, we always assume smoothness on the curve, and inside the curve in this area. So what does Green theorem say? It says if f is smooth on and inside the closed, so this is important, curve C in R2, and this is another, so I'm going to highlight these things. This is really important. So this function has to be smooth, the curve has to be closed, the curve has to be in R2, so this method doesn't work in R3. Then, so this is what the Green's theorem says. It says the integral over C f dot dr is, now please remember, if the function was conservative, this integral is what? It is always 0. Now we're not assuming conservative, we're just saying the function is smooth. So instead of doing a curve parameterization, this method says, okay, do it as a double integral over certain, we'll see what this is, df2 by dx minus df1 by dy dA. So just let me correct this. So this is x. Please remember, this is just to make things very clear. So this quantity, it reminds us of something. Remember the function, the original function is just f1, f2. Remember, if df1 by dx is, by dy is df2 by dx, the function is called conservative. The function is what? It is conservative. So imagine if the function was conservative, this is equal to this. So this is 0, so the integral is 0. This is consistent with what we know about conservative functions and path independence. Now, what is special about Green's theorem? It tells you how to compute the integral over closed curves without assuming conservative. This is the strength of Green's theorem. But here, we have a question about the orientation. So, okay, we have this closed curve. What is the orientation? Are we moving this way, counterclockwise, or is it clockwise? So we need to clarify some notation here. So let's divide this here. So C is oriented so that the interior is always to the left of a traveler along C. We need to clarify this. What is the meaning that C is oriented this way? So we're not saying, usually we say a closed curve is oriented clockwise or counterclockwise. Now what do we mean by this? Let's draw some closed curves to clarify this. This is a closed curve. This is another closed curve, but it's not this closed curve only. So we have two closed curves like that. So my curve in this case, in the second case, my curve consists of two curves One of them is like this curve, the other is this curve. Now this is the interior of the curve. Imagine somebody is walking over this curve. Imagine you are walking on this curve. If you're walking on this curve, this is your left. Here is your left. So the interior of the curve is to your left. So this is the required direction, which means you are moving, in this case, as counterclockwise. So why don't we say that, instead of saying so that the interior is always to the left, why don't we just say counterclockwise? The reason for that is, if you look at this case, this is the interior. So by definition, if you have two curves like this, the interior is the region between them. So now let's walk over this curve. If you walk over this curve, it is very clear that this is your left. But on the inner curve, you have to move the other way so that the interior is to your left. So in this case, the outer curve is counterclockwise, but the inner curve is clockwise. And this is, let's say, the only case where this orientation in the Greens theorem is not counterclockwise, only when you have the two curves cases. Yes. Okay, so this is this is the orientation of C. Now what is D? D is the interior of the curve C. So going back, this is D. This is the interior. So we always have certain area. And please remember, because we're having a double integral here, what is dA? Sorry. dA is dy dx or dx dy. Remember, whether you say dy dx or dx dy, they are the same in doing the integral. And here we just need to remember that the integral dx dy is equal to dy dx, assuming some conditions. But for our purpose, we assume the conditions fulfilled all the time, so we always have this. So this is a Greens theorem. So simply remember, the main idea of a Greens theorem is to convert the line integral. This is the line integral. So instead of doing it using curve parameterization, we're doing it as a double integral. Now the question is it easier to do it as a line integral or a double integral? That depends. So sometimes we will see, sometimes it's easier to do the line integral using parameterization. Other times it's easier to do it as a double integral. And now let's see